Hi everyone, my name is Hengbo Ma. Today I will present our paper, Multi-Objective Diverse Human Motion Prediction with Knowledge Distillation. This work is conducted by Hengbo Ma, Jiachen Li, Ramtin Hosaini, Masayoshi Tomizuka, and Chuiho Choi. Human motion prediction is important in many scenarios. There are two challenges in this problem, improving accuracy and diversity. The current literature focuses on two directions, improving prediction accuracy and improving diversity. The existing methods mainly focus on learning one sampler. Usually, if we don't improve diversity intentionally, mode collapse may happen. However, if we use the diversity loss, although the samples may be more diverse, the estimated distribution will be shifted from the data. Hence, the accuracy of prediction will be decreased. In some scenarios, sometimes we need to sample the possible future pulses which focus more on the major modes or reflect the ground truth distribution, and sometimes we simply want to investigate the diverse minor modes. In order to fulfill such requirements, a method should be able to adjust the ratio between accuracy samples and diversity samples during the testing time. Hence, in this work, we propose to jointly learn two different samplers. For human motion data, there is only one ground truth future pulses given one historical observation. In order to obtain possible diverse future pulses, several current works explore the diverse future pulses by using a similarity clustering technique. First, the similar pulses at the current time step will be grouped, and their future pulses will be considered as the possible ones for any initial pulses in the group. We suggest that such a logic can be recursively applied at any time step, and hence we can explore the diversity along the time axis. In our work, we will show how we use such a strategy to supervise our diversity sampler. Let's see the problem formulation. We intend to estimate the future pulses X distribution P given the observation C. J is the latent variable that represents different modes of future pulses. In this work, we investigate how to obtain these two prior distributions. Our framework is constructed by recurrent neural network-based conditional variational autoencoder. We use two different loss functions during the training phase to update the accuracy prior and the diversity prior separately. For the accuracy sampler, the future pulses and the history pulses are embedded in the latent space, and the predicted future pulses are generated by a decoder for training. We use a similar loss to CVAE, but with the conditional prior QACC J given C, which is the accuracy prior, to increase the power of representation. Meanwhile, we use the best of many loss as a regularization for the accuracy prior. For the diversity sampler, we use the same decoder but with a different diversity prior function to generate the future pulses. Then, we calculate the diversity sampler loss among the diversity samples and accuracy samples. At the same time, we use the short-term algorithm to supervise the diversity samples. Let's see some details. The diversity loss is used to increase the pairwise distance between the samples. The diversity loss has two terms. The first term means that we intend to increase the distance between the accuracy samples and the diversity samples. The second term means that we intend to increase the pairwise distance among the samples generated from the diversity sampler. Here, we do not allow the loss backpropagate to the accuracy prior. Only using the diversity loss is not enough. We still need some supervision from the data to make the prediction more real. For instance, we first generate one sample of predicted future pulses from the diversity prior, which is demonstrated by the blue line here. Then at time t, we use the predicted pulse xt as the input of an oracle. The oracle model will provide several possible future pulses as references with a short horizon tau. The predicted pulses in the time horizon tau only need to be similar to one of the references. This procedure is applied recursively along the time axis. Then we can generate arbitrary numbers of samples from accuracy prior and diversity prior during the testing phase. We use two datasets to evaluate the performance of our algorithm and common metrics. We can see that our methods can achieve good performance in both metrics. There is an example of our prediction results. We can see that the samples from the accuracy prior can be more close to the ground truth, while the samples from the diversity prior explore more different modes. There is another example. We can see how the different metrics change with respect to the number of samples from the accuracy sampler in the left figure. From the right tables, we can see that using a short-term oracle improves the diversity more than the method with a non-short-term oracle. It validates that recursively exploring diverse pulses along the time axis is useful. In the future, we can incorporate several existing advanced prediction models such as GNN-based ones in our framework. Also, designing a more suitable evaluation metric is necessary. Thank you.